thanking the organizers for organizing this meeting and then reorganizing this meeting, and finally for inviting me. So today I'd like to talk about some integrable delay differential equations. So by a delay differential equation, I mean an equation for a function of one variable that relates derivatives of the function and also its shifts. Okay, so f and f prime at z and at z plus 1, for example. A number of people who've contributed in a number of ways. Bjorn Bunsen from KTH in Stockholm, Zhibao Huang from the South China Normal University, Risto Korhonen from the University of Eastern Finland, Alexander Stokes from the University of Tokyo, and Jun Wang from Fudan University in China. So very briefly, delay or differential delay equations arise in many important applications, although I'm not actually sure if the types of equations, the hopefully integrable equations I'll be describing will arise in those applications, but certainly they appear in sorts of applications where you have quantities that vary both kind of locally in time and also in some sense seasonal. So what was happening at the same time last year has some effect. So differential delay equations are common in, for example, mathematical biology and finance and so on. But as I say, the equations that we're looking at, some of them are known to come from integrable systems, and the basic idea is that we're hunting for others as well, and they may or may not be related to applications. We don't know at this point in time. So a number have been found as reductions of integrable equations. So we presume that they're integrable. They have associated linear problems, although they haven't really been exploited properly to date. And what we'll be describing is a number of ways that you can derive such equations, and also ways that seem to single these equations out from other equations, and some of the interesting properties that have been observed. So kind of the canonical example I'll mention a number of times is this one. So it's 30 years old now. So this was found in a paper by Quispel, Capel, and Sacher-Deven. So they found this equation as a reduction of the Katz-van Moerbeker or Manikov equation. So it comes from an integrable system, presumably it is one, and it has a continuum limit to the first Painlevé equation. So this is what we'd like to consider to be some kind of a delay Painlevé equation. There's also an associated linear problem. We'll describe a little bit how some delay equations can be obtained by playing around with the Bäcklund transformations for the Painlevé equations. But the main question I'd like to address is, how can we look for more examples? What seems to be special about them, based, of course, on what happens for differential and difference or discrete equations. Some kind of special singularity behavior, one would imagine, lies at the heart of it. And this is at the moment still kind of a motivational question. We can partially answer it. But looking for some kind of an analog of the QRT system. So the QRT system, Quispel, Roberts, Thomson, is a system of equations that solve discrete equations solved by elliptic functions. And the nice thing about that is that it's often a starting point for looking for discrete Painlevé equations. So in many ways, Painlevé equations or Painlevé transcendence can be thought of as slightly messed up elliptic functions. So looking for equations that have solutions with lots of elliptic functions seems a natural place to start. Okay, so some of these equations that have appeared in the literature, I've already mentioned the Quispel, Capel, Sacher-Deven equation. So again, it's a reduction of Manikov or Katz-van Moerbeker. Grammaticus, Romani, and Morera used an analog of singularity confinement. So I'll describe singularity confinement a little bit later, to look at so-called Bi-Riccati type delay equations. So Bi-Riccati equation is an equation that relates, say, w of z plus 1, and their first derivatives in such a way that to upshift, so to go from the z variable to the z plus 1 variable, involves solving a Riccati equation for w of z plus 1. And it also, if you were to iterate the other way, so if you're trying to recover w of z, if you know wz plus 1 and its derivative, you'd have to solve a Riccati equation or a degenerate linear equation to iterate down, and then hence the name Bi-Riccati. So Levin-Winternitz looked at some symmetry reductions of Toda and obtained such equations, and Joshi also looked at reductions of Toda, so with a slightly more general ansatz. And Fedorov, Godoy, and Pickering have considered hierarchies of delay equations. So there are two types of delay equations that I'll be referring to, two general types. The interesting thing is that, well, obviously differential delay equations are in general neither a differential equation nor a delay equation, but some types behave a little bit more like a differential equation, and some types seem to behave a little bit more like delay equations, but of course they're neither, they're something new. So the type that behaves a bit more like a difference equation, or at least a type that behaves that way, is this one. Okay, so what's nice about this equation is that I can solve algebraically for u of z plus 1, given u of z minus 1 and u at z and its derivative. When I haven't put an argument here, it's just at z. And similarly, I could shift downwards, so I could solve for y of z minus 1, get a unique algebraic answer in terms of the other guy. So iterating such an equation is very similar to iterating a discrete equation, but of course you have to involve the derivatives, and each time you increment, you need more derivatives at your original points in order to have enough information to continue the iteration process. So kind of the jet space at your two initial conditions, so at z0 and z0 plus 1, let's say, would have to increase. In other words, you have to keep the memory of more and more derivatives at those points in order to be able to iterate out further and further. But because we have derivatives, we're looking at this as a function of one variable, it seems natural that really we should be looking at these things as functions that exist either on the whole line or in the whole complex plane. Basically, I'll be looking in the complex plane. So because this kind of iterates like a difference equation, there is a natural notion of singularity confinement or singularity confinement type arguments that can be used. The other class of equations that I've already mentioned are these Bi-Riccati equations. So this is the general form here. If I take u of z to be the vector consisting of the derivatives and the powers up to power 2 of u at z, and I just form this quantity where A is a constant matrix, then this is the general form of the Bi-Riccati equation. And again, it's characterized by the idea that to solve for little u at z plus 1, I just need u at z in its derivative, and it's a Riccati equation to do so locally, and the same going back the other way. When I say Riccati, I'm also including the degenerate case where it's linear. So even if we think of the simplest case of a differential delay equation, we can already see how things are significantly more complicated than they are for either differential or difference equations. So obviously the key thing with differential and difference equations, discrete equations, is to find some conserved quantities when they're there, which are quantities where basically the derivative vanishes or the difference vanishes. It's very easy to interpret what that means. When we have a simple linear equation involving just both a shift and a derivative, things already start to get much more complicated. So obviously, e to the lambda z is a solution of this equation, provided lambda solves a certain equation. But this equation, of course, is hopelessly transcendental. Okay, so things are much more complicated. You can see here that, so of course, if the series converges, I can construct something like this. And of course, as k tends to 0, then the lambda n's turn to integer multiples of 2 pi I, and this becomes a Fourier series. But of course, it's a much more complicated object when that's not the case. So one way in which one can derive discrete Painlevé equations is as symmetries or Bäcklund transformations of genuine differential Painlevé equations. So here's a simple example that goes way back. So for Foucault, I'm following Foucault, Grammaticus, and Romani. So if you take the third Painlevé equation, where gamma is equal to 0, and as long as these guys are not 0, I can rescale and make them 1. So I end up with an equation that depends on a single parameter, beta. And then there are two Bäcklund transformations that we can write. Well, there are other transformations as well, but here are two Bäcklund transformations. So if I start off with this, with a solution of this equation, with parameter beta, and I construct this object, then this will also solve the same equation, except beta here is replaced by beta plus 2. And I can do a similar thing, which is going to give me beta minus 1. Now, what you can do here is you can take a combination that cancels out these derivatives. So if I just take the sum of these two things, I'm left with this equation. And notice that this is a pure discrete equation. Okay, so here the roles of what is the independent variable, what's the parameter, have been reversed. So here x is the independent variable, beta is the parameter. Now x is just along for the ride. Everything is just evaluated at x. There are no derivatives or anything with respect to x. But it's a difference equation in beta. So beta is the independent variable. You can do something similar with the same transformations by taking the difference. So if you take the difference, you end up with this equation. Now this still involves shifts with beta and derivatives with x. But if you take a simple reduction, then you end up with this equation that we have here. So this equation is also a reduction of an integrable equation, and it has a continuum limit to Painlevé 1. So this is again a decent candidate for a differential, for a Painlevé differential delay equation. You can also construct examples that give Bi-Riccati type equations. So again, playing around with the same Bäcklund transformation. If I take this Bäcklund transformation, I wrote down a pair of Bäcklund transformations. Originally, the second one, which gave us beta minus 1, if we just change beta to beta plus 2, sorry, gave us beta minus 2, and if I change beta to beta plus 2, then I get another equation relating these guys. So again, if I take the difference, I get an equation of this form, and again, there's a reduction which gives us a Bi-Riccati type equation. Again, it's again, as I say, Bi-Riccati, I'm including kind of, in this sense, bilinear. Okay, so it's a linear differential equation to find u of z plus h in terms of u of z. And again, this equation has some continuum limit to the first Painlevé equation. Okay, and you can play the game again. Maybe it's not interesting to see another example, but we can construct similar examples by playing around with Bäcklund transformations. So since these things are coming from Painlevé equations, they have continuum limits to Painlevé equations, and some of them are already known to come as reductions in their own right directly from other integrable differential delay equations. Other places to look for integrable equations is again based on the analogy maybe with the QRT system that I was describing earlier, is to look for equations that are solved, well, that have lots of solutions, let me put it that way, in terms of elliptic functions. So for example, we all know that the Weierstrass P function satisfies this equation. If we write down the addition law for the Weierstrass P function, then it's very easy to see that U solves this equation. So this is very similar to an equation that I've already written down. Okay, so if I kind of just added in U of Z in here, then this is an equation that we've already seen that has a continuum limit to the Painlevé equation. So this is something like the autonomous version of that, although notice all of the equations that we've actually looked at so far, even the ones that have continuum limits to the Painlevé equations, are actually autonomous. That's because in the continuum limit, at least the equations we've talked about so far give us something, give us the first Painlevé equation, the continuum limit. The continuum limits that we get actually give us a third order differential equation that then you integrate once to get the first Painlevé equation, and that's where it kind of de-autonomizes, if you like. The QRT system, which I've already mentioned a couple of times, is a family of discrete equations. So here I'm just looking at the symmetric QRT system. This is not the most general one, but it's very quick to describe. So basically, if I want to solve for the n plus first iterate, it's a Möbius transformation in the n minus first iterate with the various coefficient functions being polynomials in X. And the way that those polynomials are constructed is in this slightly odd-looking way. You take a couple of general symmetric matrices, you multiply them by these x's, you take the cross products, and the different components give you these different f's. And the main thing about this construction is it has a conserved quantity. Okay, so you can show that this quantity is conserved. So really, everything lies on elliptic curves for first order curves, it's clear what we mean by this. We just need to show that k shifted upwards is equal to k shifted downwards. But as I've already mentioned, for the differential delay equation, getting a natural analog of that, it doesn't lead to just trivial equations. Obviously, we could have the same thing. We could have the shift invariant, or we could have the derivative invariant. That doesn't seem to give us anywhere near the generality to play the games that we would like to play. So a natural kind of analog of this thing, since generically the solutions of such equations are Möbius transformations in the Sn functions, is to look for equations that have lots of solutions of this form. So here, if we're looking for the this delay or difference type equation, shall we call it, the type that you can iterate easily without having to solve differential equations. So examples of such a thing are easily constructed using the addition laws for the elliptic curves. Okay, so again, this equation is basically the addition law for the Sn function, or at least adding, taking the difference of two such quantities in here. Now, it's easy to construct lots of examples of such equations, but they will, in general, just have a one-parameter family of solutions. Since they're autonomous, I can always shift z by something. But for these to be analogues, presumably, of what happens with the QRT system, we would like to have something that's at least a two-parameter family. So the game that was played with Bjorn Bernsen, a former PhD student of mine, was to look for classes of equations that have at least a two-parameter family of solutions in terms of elliptic functions. So in Bjorn's thesis, he found a number of equations of this form. You can also play the same game with the Bi-Riccati equation. So again, remember the Bi-Riccati equations are of this form, where k is an arbitrary matrix. And the idea that we're looking for here is we want a two-parameter family of solutions. One, of course, because it's autonomous, I can always shift the z. So what we would like is to take some Möbius transformation where now we can vary everything with respect to another parameter. Okay, so in other words, if we ignore the shift in the z, we're looking for a one-parameter family of solutions like this, where I'm not shifting z. So a simpler example is to ask ourselves, well, when do I have an equation that's just solved by Sn itself, okay, rather than a Möbius transformation in Sn? So that's easily done, okay? So I take Sn and I substitute it in here, and then I use lots of the identities that we know for the addition laws and the various equations that Sn has to satisfy. And we actually see that if I expand out this left-hand side, it's basically a linear combination of 7 equations, in the sense that I have some arbitrary coefficients in here, and then each of those different terms would individually vanish. So the x's here I've written out in this form. What do I expect you to see from this? Well, firstly, I should just explain that S, C, etc. These are just the Sn functions, etc., evaluated at this point omega h. So these are just these are the h is the step size, and omega and k just some fixed constants. The other thing to notice is that these terms here in the last row and the last column, these are the things that drive derivatives. Okay, so these are things that when I expand out the equation, they would correspond to the existence of a term involving a derivative, or in this case, two derivatives. It would be a derivative of both, the product of derivatives of the two terms, the upshift and the unshifted guy. So one thing we can see immediately is that all but the first one contain exactly one term in this bracket here. So we have just one term derivative, and this involves no derivative. So this actually corresponds to the elliptic curve. So this is just a pure difference equation. If I were to write this out in this way, okay, where I have these guys in here. So that's the special case where I have something solved in terms of Sn, but we were interested in having more general Möbius type transformations. Well, it's easy to see that the Möbius transformation acts on X, on this guy, in this way, where M is just some matrix of this form. So what we're able to do then is to come up with lots of examples of Bi-Riccati equations that have a two-parameter family of elliptic function solutions. Although I have to say, unlike the QRT system where there's conserved quantity, well, there is a conserved quantity that you can easily write down, and there's a nice geometrical picture of what's going on. We don't really have that. We have a bunch of equations, okay, but we have a bunch of equations that one could then look at different iterative schemes for. So let's move on to what kind of properties we could be looking for a differential delay Painlevé equation or integrable equation. So again, sticking with the idea that since here we have derivatives and shift with respect to the one variable, it would seem natural that we're going to be treating that variable as a continuous variable. So if we come back to looking at differential equations for functions of a difference or discrete equations for equations of a continuous variable, then we come back to the idea of looking for functions in the complex domain. Now, it's been known for a very long time that if I could take an equation of this form where R is a rational function, then this equation admits a non-constant meromorphic solution. And in fact, if I take R to be a polynomial, then there admits a non-constant entire solution. So this goes back to the work of Schroeder and Witten and Julian. So in particular, even the logistic map has a non-constant entire solution. So the existence, and we can even throw in an arbitrary periodic function. So the existence of lots of entire or meromorphic solutions is obviously no kind of guarantee of anything like integrability. So the natural concept is to restrict ourselves to nice meromorphic functions, and the natural characterization of a nice meromorphic function is that of finite order coming from Nevanlinna theory. Don't worry, I'm not going to kind of drown you in Nevanlinna theory. These are pretty much the only true Nevanlinna formulas that I'll be putting up here, and this is just to give you a very brief understanding of what it's about. So the idea in Nevanlinna theory is to take a meromorphic function. By that I mean a function that's meromorphic in the whole complex plane. And we want to, having fixed that function f, we want to look at that function on a disk of radius r. So that's what this thing is here. And then, so t for fixed function f, t is a real valued function of r, and r is the radius of this circle. And basically what we do is we're looking at the asymptotics of this function as r tends to infinity to extract lots of useful information. So in the case where f is entire, then tr of f is basically log of the maximum of f on the disk. I say basically because you can bound it above and below by something that looks very similar to this. So it's just going up with its size, basically. If I have a meromorphic function, obviously I can't do that anymore because there'll be lots of circles every time I'm on a circle that goes through a pole. Obviously that's not going to work. But we have a term that kind of plays the role of this thing. This is called the proximity function. And this measures, in a sense, how close f gets to infinity, or how big it is on a certain on a circle. And it's basically if you take the log of the modulus of f on the circle, so not the disk, but the circle, if you take the log of the modulus of f and cut out all the negative values, so wherever the log becomes negative, or wherever the modulus of f gets less than 1, you just set this function to be 0, and you just keep the bigger bits, and you take the average of that on the circle, and that's exactly what this is. But the upshot is that it's a measure of how big f is. Okay, so if f gets kind of big on big parts of circles, then this is big. And similarly, n is a measure of the number of poles inside the disk. You won't lose too much if you think of it as actually the number of poles inside the disk. It is actually the number, you're actually integrating that number, the number of poles, logarithmically as you go out. But basically, if you've got lots of poles, this term is big. So the only way that this gets big is either if my function is big, for chunks of the circle of radius r, or there are lots of poles inside the disk of radius r. And then the order of f is simply a measure of how quickly this thing grows. So the actual order is just the lim sup of the log of this divided by the log of r. So in other words, if t grows like r to some power, then that power is the order. And there's also something called the hyperorder, where we chuck on an extra log. So the reason I'm talking about this, originally we talked about finite order functions, but basically all of the proofs that we have, you can assume something weaker, which you can assume a little bit bigger growth. So you can assume that the hyperorder is less than 1. So these are examples of finite order functions. Okay, so exponentials and trig functions and any elliptic function. Infinite order functions are these guys. Okay, so the exponential of an exponential. This thing would be hyperorder 1. So that's going to be a little bit too big for our taste. But a function like this would be hyperorder 1/2. Okay, so cos of the root of z is something of order 1/2. It's an entire function, of course, so the branching cancels out because you only ever see the square root of z as square root of z squared, or z. So this thing is of hyperorder 1/2. So that's infinite order, but not too bad. Okay, 1 seems to be the dividing point. So if we come back to our example of a first order equation, and we demand that not only does it have a meromorphic solution, because they all do, but it has a non-rational meromorphic solution of finite order, then the degree here actually has to be 1. In other words, the maximum of P and Q here has to be 1, which means that we reduce to this equation. And this is, of course, the discrete Riccati equation. It can be linearized by a discrete logarithmic derivative type substitution, just like the common or garden variety Riccati equation. So we will have this annoying habit where we have, if I have rational coefficients here, in order for us to say anything about it, using Nevanlinna theory at least, I need the solution of the equation to be more complicated than rational. That's what in general we'll call admissible. Okay, so when it's rational coefficients, admissible corresponds exactly to a non-rational meromorphic solution. In general, it means that the characteristic function of this grows a lot faster than the characteristic function of this. But again, we don't need to dwell on that. So Risto Korhonen and I, sorry, I should have mentioned. So with Abelitz and Hodge, so we suggested that the Painlevé, a natural analog of Painlevé property for difference equations, was finite order meromorphic growth. And Risto Korhonen and I looked at equations of this form, where R is a rational function in W with meromorphic coefficients in Z. So again, as long as I assume that W grows faster in the sense of Nevanlinna than those coefficients, then either it turns out that W solves a Riccati equation, or it's one of these things, which are basically the difference analogues of the known discrete Painlevé equations. These pi's here are arbitrary periodic functions, which you'd have to have in a setting. So let's come back to differential delay equations, because obviously this idea just translates directly into differential delay equations. You can ask yourself the same question. So when do you have finite order, or in this, as we now know, hyperorder less than 1 is enough for all those theorems to go through. So if we take hyperorder strictly less than 1, so with Risto-Korhonen in 2017, we looked at equations of this type. Why this type? Well, because we knew that when this thing is a constant, that contains one of these Painlevé 1 equations. So we just wanted to see if we could pull that out, if we could find anything else. So if we take equations of this form, unfortunately, there are lots of extra technical conditions that are thrown up when you start looking at these equations with both shifts and derivatives. One thing is that, although it's not something I'm going to be talking about today explicitly, but basically in Nevanlinna theory, you can show that the function that you have in general takes the singular values that you need it to take, so that you can actually extract useful information from the usual kind of arguments that we use, which are things like singularity, confinement. Some of those arguments don't always work in this sort of setting, so we're currently trying to push that a little bit. But at least what we were able to show was that initially the degree of this thing has to be strictly less than 4. And if we take the case where the denominator here does not have a simple factor W, then we can say more about the general form of the right-hand side. Well, one reason why this is an issue, that this would mean if this is allowed to be 0, if I had a 1 over W term sitting in here, then I can have a balance of poles between these two things, which creates problems. And again, also this argument I was just saying from the pure Nevanlinna side, I wouldn't know that I necessarily have enough zeros for the calculations to go ahead. If we restrict ourselves to this equation where we allow A and Z and B to be functions of Z, and again, we assume that there's a hyperorder less than 1 solution, but now we need to add in an extra condition that there are a lot of simple zeros. So in our previous work, we were able to prove this, but here we had to have it as an assumption. And there's a reason why you have to have it as an assumption, because well, there are equations of this form with solutions that look like this. Okay, because basically I could have, if I have this relationship between A and B, I can basically have this bit satisfied by an exponential and this bit satisfied by the same exponential. So this kind of breaks up trivially for this one solution into a difference equation and a differential equation that can both be simultaneously satisfied. And that creates some technical issues that aren't there for pure differential or for pure delay equations, at least in general. What we mean by lots of simple zeros, if you know any Nevanlinna theory, is this thing. Okay, so I won't really say much more. But it basically says that if you ignore multiplicities, you've got to have at least 3/4 of the maximum number of zeros that you could possibly have in some sense. Basically, meromorphic functions for arbitrary values take all values at some kind of upper limit, upper rate in disks as you move out, but there can be special values where that's not true. And if that disk happens to be one of those special values, then we can't run the arguments in the way that we would like to. So also, if we look at a slightly different class, so here we have a square on the bottom. So the other theorem we looked at didn't have a square. We just had power 1. If we have a look at this equation, actually, we were able to find some non-autonomous equations that appear to have hyperorder less than 1 meromorphic solutions. I have to say at this point, these are necessary conditions that we're obtaining. None of these results are giving us actual existence until we push things further, but just as is the case with differential and discrete Painlevé properties, at least in the case, we can often pull out these things solved by elliptic functions. We're left with other things that have continuum limits to Painlevé equations, but we can't say for certain at the moment that they genuinely have these meromorphic solutions, although I think they do. So the main, as I said, I'm not going to talk much about the kind of technicality of doing Nevanlinna theory, but the upshot is often for both the difference and the delay equations is that you want to use Nevanlinna theory that basically says that these certain values we can expect some kind of even distribution. Very roughly speaking, in a big circle, for example, maybe the solution of your equation should roughly have equally many zeros and equally many poles, and there should be a lot of them. And that's true of most things, and that can be proved for a lot of equations. And then you need to, and then the contradiction comes by effectively using something that looks like singularity confinement, or in our case, more precisely, singularity non-confinement, and showing that you don't have that property. So therefore you get a contradiction unless something very special happens. And that's how we arrive at our necessary condition. So let me just give you a brief idea of how that works in the pure difference setting. Now here, I'm going to do a little bit of a cheat, because if I were to do this as an actual difference equation, then I'd be thinking of n as z, as the independent variable, and you get all sorts of technicalities where I can have locally some kind of vanishing because A takes on some special value somewhere, or B takes on some special value somewhere. But as Risto, Cohen, and I realized, the types of methods that we were using in Nevanlinna theory actually give us a really simple way of calculating entropy, so kind of algebraic entropy, that really is essentially nothing more than the standard singularity confinement calculations that people have been doing for decades. So let me briefly remind you, or tell you if you haven't seen before, exactly what singularity confinement is. So this goes back to Grammaticus, Romani, and Papageorgiou for the description of the method, and then the actual discovery of many discrete Painlevé equations was in this second second paper. So the basic idea here is that you want to look at what happens when you iterate in equations through a singularity. So here you can imagine if you're going from finite values, you'll hit infinity if you hit the value +1, -1. Now, it's not really the fact that you go to infinity. There actually isn't anything too remarkable about infinity, but it's the problem that in general, if I hit a certain value as my final iterate, it doesn't tell me much individually about the previous values, just that there's some relationship between them. But something very special happens here, because the one step back, you could have any finite value that you like, but if the next value is 1, then you know that you're going to hit infinity at the next level. Okay, so it's singular in this sense. And in general, what happens there is as you iterate, you keep cycling through these special values, 1, -1, and infinity. So let's have a quick look at how that happens. So the basic idea would be to start off with these initial conditions. So k can be anything finite, theta is ±1. We just bump it a little bit. So we stick in an epsilon, we iterate, we keep the first few terms in some Laurent series, and then we look at what happens as epsilon goes to 0. And you can see we go to theta, again, so ±1. Then I go to infinity, then I come back to -1, 1. And then in general, I'd go to infinity again. But what could happen is that I could terminate that by making this thing vanish for all n and for both signs of theta. So if I do that, this decouples into 2 independent equations. The reason we want that for all of them is we don't want any solution that has this behavior that you keep iterating along. So the only way to do that is to have these vanish identically. That gives you 2 linear equations for A and B. That gives you this equation. And this is an equation with a continuum limit to the second Painlevé equation. Some would just call it the discrete second Painlevé equation. And it has all sorts of nice properties like Lax pairs. But the classic example, this equation seems to have the same property. Okay, so we start off with some finite value. We hit 0. we have a couple of infinities, but just two. Then we come back to 0, and then we're out again. So it seems to be confined in that same sense. But this equation is known to be chaotic. It's not integrable. And numerically, you can see that it's chaotic. So one other way of distinguishing integrable equations is by looking at various growth rates of complexity, of which Nevanlinna is yet another one. But one way, of course, you can look at these equations. Technically, you should look at them on projective space. But if I just think of iterating this rational equation a few times, then if I start off with initial conditions y0, y1, and I keep iterating, the nth iterate is going to be some rational function y0 and y1, and I can just look at how its degree grows. And in general, the degree grows exponentially, but for these special, and it does here too, but for these special equations, like this one, it doesn't. It grows polynomially, and that's, again, this low complexity growth. So calculating that exactly, so calculating it in practice is relatively easy because you do a few examples and you fit it to something numerically, and then you can work out what's happening. But to prove it can be complicated. But it turns out that at least if we work in a slightly different way, we can calculate this number doing nothing more than the calculation that we've already done. Okay, so all the hard work was in the singularity confinement calculation. So what we're going to do is that y0 and y1, when we're looking at rational functions of them, we're going to choose y0 and y1 both to be rational functions of some other parameter. Okay, and we're going to see how so then everything becomes a function of one variable, but we haven't specified exactly how they're rational functions of them, but you know, but now we've reduced everything to a function of one variable, and calculating degrees and so on for functions of one variable is a lot easier to keep track of. So just one kind of trivial thing, if you have a rational function ratio of two polynomials with no common factors, then there are two equivalent, of course, notions of degree. One is just the maximum of the degree of the two polynomials, and the other one is in thinking of rational function as a map between, from the complex sphere to itself, it's the number of pre-images, counting multiplicities, of any value that you care to take on the sphere. So, for example, if I take this thing, it's obviously of degree 5, okay, because that's the maximum of the degree of the two polynomials. But if I expand it out like this, and I want to look at the pre-images, say, of infinity, well, and you can also see the number of pre-images of 0 would be 5, but the number of pre-images of infinity, well, here I have a simple pre-image of infinity when x is 0. When x is 1, that's also a pre-image of infinity, but it is to the power 2, so it's counted twice. And similarly, infinity is a pre-image of infinity, again, of multiplicity 2, so 1 plus 2 plus 2 is 5. Okay, so we have these two ways of calculating degrees. With that in mind, it's very easy to calculate the degree growth as I was describing. This is the calculation that I had written down earlier. I've just added two things. I've added a little o of 1, because what I'm doing here is I'm thinking of an expansion around some point now, z0, and the eps and all of these things now represent series expansions in this extra parameter z, and the small function we've been perturbing around is really just the non-constant part of this series. So what it's telling me is that yn at z0, yn takes the value theta plus or minus 1 with multiplicity p. Okay, so now this is the same calculation that we had before, no change whatsoever. And again, if I, so I can see that here I hit the value theta with multiplicity p, then I have a pole with the same multiplicity. So this is critical here. Then I come out with minus theta with the same multiplicity. And now here, and that's why it's important that we take the whole series, not just the next term, I can see if this thing vanishes, again, I'm back to finite values. So the whole idea of this calculation then summarizes as, if I start from finite values, the only way that I can hit infinity is if the previous term is plus or minus 1. And if that happens, I will have a pole of the same multiplicity minus theta of the same multiplicity, and then I'm going to be out. And then we just have to worry about what happens at infinity. So if I choose my initial condition such that the both initial conditions are proportional to z, that means that they have a simple pole at infinity, then every subsequent iterate, it's very easy to see, has a simple pole at infinity, which is enough for this to work. So for concreteness, I could just take y0 and y1 to be affine in z, just making sure the coefficients of z here are non-zero. And then the calculation that we've done previously is enough to tell us exactly what's happening. So here, this is supposed to represent the squished complex sphere, Riemann sphere, corresponding to y0. Y0, remember, is a degree 1 function. It was just az plus b, and so is y1. So what does that mean? It means that there's exactly one place where it hits infinity, here and here, and there are no others. If I'm interested in the infinities at this point, I know the only way that I can get a new infinity here is if I first hit a 1 or a -1 here. Well, this is of degree 1, so that tells me that there's exactly one place where I hit 1 with multiplicity 1, and exactly one place where I hit -1. And now the calculation that I had before tells me that I have these values with the same multiplicity, so multiplicity 1, and these are therefore the only infinities that I have here. They're all of multiplicity 1, so the degree is just the sum of them, so it's 3. So the degree is 3, we don't have to do any calculation. Since it's 3, that means that it hits every value 3 times, counting multiplicities. So there must be 3 points where I hit -1, 3 points where I hit +1. Counting multiplicities, so they could be, 3 separate points, 3 separate simple points, or 1 point of multiplicity 3, for example, but it doesn't affect our calculations. So the only infinities that I get here, apart from this one, which is always here, comes from these guys. So I can see that I've got a 3 here and 3 here and nothing else. So the degree of this is 7. And then finally, what's slightly different here, since the degree here is 7, the number of times I hit 1 is again 7. I've already hit 1 here once. So there's going to be another 6 here, and there's going to be another 6 -1s. So that tells me the only infinities that I get at this point is this, and I have degree 13. Okay, so you can calculate exactly what's happening with the degree as you iterate through. And of course, you can find the general setting. So if I so dn here is just the degree of yn, and capital N is the number of new +1 points. New meaning they're kind of in the left of this little cartouche, and not these guys which are in the right, which are kind of the old ones. Okay, so these are the new spontaneously developing ones. And of course, it's the same number for the -1s. So with that in mind, if I want to calculate the degree of n plus 1, it's the number of this infinity, which is 1, plus the number of these guys. Well, the number of these guys, counting multiplicities, is just the number of +1, new +1 points back here. So there's 2n of them, so I have this guy. And similarly, if I want the degree of yn, then I could calculate it a different way. I could calculate it from the number of pre-images of 1. So there are capital N new ones, and then there are these old ones. Okay, well, the old ones come from the infinity in this cartouche at the previous step. How many of them were there? Well, it's the degree of this. Okay, so that's dn -1. You subtract off 1 to get rid of this guy, divide by 2 because we've got this, and you have this expression. So I have these two expressions. I can now eliminate the capital N to get this. My initial conditions were that I had 2 affine functions, so the degrees were both 1. So I have an exact formula that tells me the degree for all future terms, and you can see that it grows quadratically exactly. And if we briefly come up to Hietarinta, I'm going to have to go a little bit faster, but if we come up to the Hietarinta case again, I can interpret it the same way. So the upshot here is that the only time I can get to infinities is by first having a 0. If I have a 0 of a certain multiplicity, I'm going to have a pole of double that multiplicity, again, double that multiplicity, 0 of the same multiplicity amount. And you can see this discrepancy, and this is what drives the problem. I've got twice as many poles counting multiplicities as I do zeros, and that's the sign of trouble. If I play the same game, that everything's going to have a simple pole at infinity by choosing my initial conditions, then we can calculate things exactly. Here is a picture where the algebraic entropy was calculated rigorously using blow-up. So there you can rigorously desingularize the whole situation, and then you're looking at the behavior of the Picard group to get the algebraic entropy is this, but you need 14 different blow-ups to do that. But we can play the same kind of games I just played before. I'm getting a little bit short on time, but I won't explain where these comes from, but it's the same reasoning that I used before. So we get two equations. I can eliminate the capital N's using this identity. I get a second order equation for the degrees, same initial conditions. I have an exact formula for all future iterates. Okay, it's not estimated at all. And you can see the growth has exponential base this thing, which is the algebraic entropy. Okay, so this is a little bit different from the confinement that we have in Nevanlinna theory, because there the z and the n are the same thing, and then these coefficient functions that can depend on z, which here don't because they just depend on n, you have to wonder what happens at certain points where there's some kind of cancellation, but you can control it all. It's just a pain and lots of analysis and epsilons and deltas, but it works in a very similar way, and so does the kind of singularity confinement type results, and so that's what leads to some of these calculations. So these singularity confinement type arguments in various forms are really what underlies the kind of different integrability detectors, if you like. So the rational surfaces approach, you're desingularizing around these points. Algebraic entropy, just seen a connection. Nevanlinna theory I'm describing, Diophantine integrability there, you're looking at height growth of numbers in a number field or rational numbers, but then it's the same thing here. It's just the small epsilon there is something measured periodically. And these things in particular extend to differential delay equations. It's just that now, because of those derivatives, we have to keep more terms in the power series than we did before. So in the calculations that we were looking at, that Risto Korhonen and I were looking at originally, we had these assumptions that we needed lots of simple zeros because we were only kind of looking at the iteration schemes that came from simple zeros. It's clear that different things happen for different multiplicities. So Alex Stokes did a really nice study in his thesis of the different singularity patterns that can arise when you have different, so for example, here, if I'm iterating this equation to solve yz plus 1, there's a problem when u hits 0. But the difference here is that the singularity structure is completely different depending on the multiplicity of that 0. So what we did before, it doesn't play any role, but here it does. And so, for example, he found that if you hit 0 with multiplicity m, then you'll have a string of 2m simple poles, and then you'll have another 0 of multiplicity m, and then you have a finite value out the other side, which is, again, really nice. You've got the same number of zeros and poles counting multiplicities, but you have this completely weird singularity pattern that we haven't seen anything like that before, which is really interesting, and should employing that in some of these results should also give us finer answers. I'm almost out of time, so let me just kind of add that in more recent work with Risto Korhonen and Jun Wang, we can get more precise answers to the ones that we had before. We had a number of different kind of tedious technical issues to overcome the first time around that weren't there in these other situations. So we can deal with the case where we have a 0 at the bottom, and we have some general degree bounds. When we look at the different cases, we can now prove that if you have an equation of this form where w equals 0 is not a 0 on the bottom, but it's a simple b of z is not 0, then we can show that you have very few zeros, ignoring multiplicities. That's what the little line means. And we even have some equation that the coefficients have to satisfy, although these are probably special solutions. In this is one of the other subcases that just came up in the theorem that I wrote. But looking at this equation, if we have something of slow growth, it turns out we can only have it if it's somehow trivial. It satisfies this Riccati equation, and it's not even kind of a real Riccati equation because 1 over w therefore satisfies a linear differential equation. This is maybe the more interesting case where there still might be something, because here we can show there actually are lots of zeros. We have some conditions on the on the coefficients. And the remaining case, which we haven't fully analysed, but we've just shown that there really is a finite order meromorphic solution that lives there. So since I'm basically out of time, I'm not going to say anything more about these things. Just to briefly summarize that there are a number of differential delay equations that look like they should be called delay-Painlevé equations, in that some of them come directly from integrable systems, some of them have lattice pairs, they have interesting and simple singularity structure, although there isn't a full theory to back any of this up yet. We have lots of equations that are solved in terms of elliptic functions that can presumably be the starting point for describing some of these things, and maybe there's more of a chance of having a good geometric theory in terms of that. Again, Alex Stokes has been looking at a more geometrical approach to these things rather than looking at these things as global functions, looking at the kind of analog of the Sakai-Okamoto approach. And I will just leave it possibly with a very quick advertisement, if I may be so bold, for my my online seminar series, which has just gone on break over the summer, but will restart in September. So it's on complex analysis broadly interpreted, but we often have things on Riemann-Hilbert problems and Painlevé equations and so on. So if you're interested, just drop me an email and I'll add you to the mailing list, but nothing's happening until September. Thank you.
Okay. Thank you for the nice talk. Are there any questions? So, may I ask about this differential delay Painlevé equations? So, do I understand correctly if you look at this generic Sakai picture, then we have not just one Painlevé equation, one Bäcklund transformation, but we have an entire group of translations, and to each translation we can assign some Painlevé equation. And what happens basically is just that you take some translation, which is a sum of this difference translation and kind of differential translation, and study a corresponding equation, or it's something a bit different.
Short answer is I don't know. So again, Alex Stokes has examined blowing. So basically, firstly, looking at, if you like, maybe a more naive notion of singularity confinement, and really proving that these multiplicities do what they're supposed to do, and then interpreting them in terms of local mappings to desingularize them. But I don't think there's an interpretation that we're aware of yet in terms of translations. But what you said sounds interesting. I don't know if Alex has any comments.
But is it correct that if you want to get some generic solution of this delay differential Painlevé, you can just take a generic solution either of differential Painlevé or of d-difference Painlevé, maybe choose some normalization correctly, and this solution will be also a solution of this delay differential equation.
I'd be pretty sure that that's not the case, but you know, so in general, if you look at the difference, for example, between differential Painlevé and difference Painlevé or discrete Painlevé, they're quite different beasts, and you don't usually have one thing solving the other, and you can prove that to some extent. But I guess you could explore that a little bit more precisely in the settings that are solved in terms of the elliptic functions. But even there, you know, you see they're connected by a continuum limit. They're not actual common solutions.
Well, but in the usual Panevé case, it's exactly the case, because if you have a solution of the Panevé equation dependent on this parameter beta, then it should satisfy at the same time Panevé equation, Bäcklund transformation, because they're kind of commuting flows.
Sorry, yeah, no, sorry, I see what you're saying now. So you're talking about considering a whole family of, so it's not just one fixed equation. You're considering a function both of z and its parameters. But sure, if you consider them collectively. Sorry, I misunderstood.
So, and I wanted to ask another question. So, what are the log pairs for this delay differential equations? Because it's hard to imagine this.
I won't be able to remember it, but they are a bit crazy. So I don't really know how exactly to use them. But there's one, for example, mentioned in the paper by Capel, Crispel, and Safedina. So it comes as a reduction of the Manikov or Katz-von-Moorbach equation. I can't remember the form. If I tried to write it down, I'd get it wrong. So you have a weird mix of like derivative operators and shift operators.
Okay, thank you. Are there any other questions? Okay, if now, let's thank the speaker again.
Thank you.